An impedance-grounded system with a high impedance setting, such as the one limiting fault current to 200 amps, offers several potential benefits in the described scenario. Firstly, equipment protection is enhanced. By limiting the fault current to 200 amps, the circuit breakers protecting the 480 volts transformers are less likely to trip unnecessarily during a fault, thus ensuring continuity of service. This is because the reduced fault current minimizes stress on the equipment, preventing potential damage that could arise from higher fault currents. Secondly, selective coordination becomes more achievable. In facilities with multiple power sources, selective coordination is crucial. It ensures that only the circuit experiencing the fault is tripped, preventing widespread outages. A high impedance grounding system aids this by limiting the fault current to a level below the trip current of upstream circuit breakers. This targeted approach allows for quicker restoration of service and minimizes disruption to unaffected areas. Thirdly, the risk of arc flash hazards is significantly reduced. Arc flash events are dangerous and can cause severe injuries or equipment damage. By limiting the fault current, a high impedance grounding system reduces the energy release during a fault, thereby lowering the potential for arc flash incidents. This creates a safer working environment for personnel. Fourthly, system stability is improved. High impedance grounding can prevent voltage dips or oscillations during faults by limiting the fault current. This is especially important for critical loads that require a stable power supply. The system is less likely to experience disruptions, ensuring reliable power delivery. Fifthly, compliance with codes and standards may necessitate such a system. Standards like IEEE 1584 may require impedance grounding in specific situations. The 36 ohms impedance setting, limiting fault current to 200 amps, could be a requirement to adhere to these regulations. It's vital to remember that high impedance grounding does not eliminate the need for comprehensive fault protection measures. Circuit breakers and other protective devices must be properly sized and coordinated to ensure selective operation and prevent damage to both equipment and personnel. The grounding impedance, in this case 36 ohms, is chosen to limit the ground fault current to a specific level. This level is a trade-off between several factors. Firstly, it must be low enough to allow protective devices, such as ground fault relays, to quickly detect and isolate ground faults. Secondly, it must be high enough to limit the magnitude of ground fault current, thereby reducing the risk of damage to equipment and personnel. Thirdly, the choice of impedance is influenced by system characteristics, including voltage level, transformer size, and the length of conductors. Finally, coordination studies are essential to determine the optimal impedance value that achieves the desired balance between protection and performance. Let's examine the role of each component in the system. The 12,470 volts ungrounded service from the utility transformer initially feeds into a service disconnect. This disconnect serves as the main point of isolation for the entire electrical system, allowing for safe maintenance and repairs. After the disconnect, the power flows to a transfer switch connected to a 12,470 over 7,200 volts 2.5 megawatt generator. This transfer switch is a critical component as it allows for seamless switching between the utility power and the generator, ensuring uninterrupted power supply during utility outages. The generator itself is impedance grounded using a 36 ohms resistor, limiting the ground fault current to 200 amps. As mentioned before, this impedance grounding provides several benefits, including reduced arc flash hazard, improved system stability, and enhanced equipment protection. The 12,470 volts equipment downstream of the transfer switch consists of transformers, specifically 12,470 to 4,160 volts transformers and 12,470 to 480 volts transformers. These transformers step down the voltage to levels suitable for various loads within the facility. The circuit breakers protecting the primary side of the 480 volts transformers are rated less than 200 amps, which aligns with the limited ground fault current provided by the impedance grounding system. This ensures that the breakers can effectively interrupt ground faults without causing unnecessary tripping of upstream breakers. Consider the specific example of a ground fault occurring on the 480-volt side of one of the transformers. Without impedance grounding, the ground fault current could be very high, potentially reaching thousands of amps. This high current could cause significant damage to the transformer, conductors, and other equipment. It could also create a severe arc flash hazard, endangering personnel in the area. With the 36 ohms impedance grounding in place, the ground fault current is limited to 200 amps. This reduced current minimizes the risk of equipment damage and arc flash hazards. The circuit breaker protecting the transformer is designed to trip at or below 200 amps, quickly isolating the fault and preventing further damage. Furthermore, the limited ground fault current helps to prevent voltage dips and oscillations in the system, ensuring stable power supply to other loads. The 200 amps fault current is also beneficial for pinpointing ground faults. It provides a measurable current to trace for troubleshooting purposes. Without it, the low current would be very difficult to find. The choice of 36 ohms impedance is a calculated value that depends on multiple factors. Firstly, the system voltage is a primary factor. Higher voltage systems generally require higher impedance values to achieve the desired ground fault current limitation. Secondly, the size and capacity of the generator and transformers also influence the impedance selection. Larger generators and transformers may require lower impedance values to ensure adequate protection. Thirdly, the coordination requirements of the electrical system must be considered. The impedance value must be chosen to allow for selective coordination between the ground fault relays and circuit breakers. Finally, the applicable codes and standards, such as IEEE 1584, provide guidance on the selection of impedance values for different types of electrical systems. Understanding the purpose and benefits of impedance grounding is essential for designing, installing, and maintaining safe and reliable electrical systems. While limiting ground fault currents, impedance grounding helps to protect equipment, reduce arc flash hazards, improve system stability, and ensure compliance with applicable codes and standards. In summary, the use of a high impedance grounding system with a 36 ohms impedance, limiting the fault current to 200 amps, is a deliberate design choice aimed at achieving multiple objectives. These objectives include protecting equipment from damage during ground faults, enabling selective coordination of protective devices, reducing the potential for arc flash hazards, improving system stability by minimizing voltage dips, and complying with relevant codes and standards. While the 200 amps fault current might seem high at first glance, it is a carefully selected value that balances the need for effective fault detection and isolation with the desire to minimize the risks associated with high fault currents. A proper understanding of these considerations is crucial for ensuring the safe and reliable operation of the electrical system. The 12,470 volts ungrounded service presents unique challenges and considerations compared to grounded systems. In an ungrounded system, a single ground fault will not cause the circuit breaker to trip. Instead, the system will continue to operate with one phase grounded. This can be advantageous in certain situations where immediate shutdown is undesirable, such as in critical industrial processes. However, it also introduces the risk of a second ground fault occurring on a different phase, which can lead to a phase-to-phase fault with potentially high fault currents. To mitigate this risk, ungrounded systems often employ ground detection devices that provide an alarm when a ground fault occurs. This allows personnel to identify and correct the fault before a second fault occurs. The impedance grounding system, in contrast, provides a controlled ground path for fault currents, allowing for selective tripping of circuit breakers and minimizing the risk of high fault currents. The choice between an ungrounded system and an impedance grounded system depends on various factors, including the specific application, the criticality of the loads, and the risk tolerance of the facility. In the described scenario, the impedance grounded system was likely chosen to provide a balance between the benefits of both ungrounded and grounded system. It allows for continued operation during a single ground fault while also providing protection against high fault currents and arc flash hazards. The 2.5 megawatt generator in the system plays a crucial role in providing backup power during utility outages. The generator is impedance grounded using the same 36 ohms resistor as the utility service. This ensures that the grounding schema is consistent regardless of the power source. The generator's grounding system is designed to work in conjunction with the utility's grounding system to provide reliable fault protection. When the transfer switch is in the generator position, the generator's grounding system takes over and provides the necessary ground path for fault currents. The 12,470 volts to 4,160 volts and 12,470 volts to 480 volts transformers are essential components in stepping down the voltage to levels suitable for various loads within the facility. These transformers are designed to withstand the stresses associated with the impedance-grounded system. They are typically equipped with surge arresters to protect against voltage transients and other overvoltage conditions. The transformers also have their own overcurrent protection devices such as fuses or circuit breakers to protect against faults within the transformer itself. The coordination of these overcurrent protection devices with the ground fault protection system is crucial for ensuring selective tripping and preventing unnecessary outages. The circuit breakers protecting the primary side of the 480 volts transformers are rated less than 200 amps. This rating is chosen to align with the limited ground fault current provided by the impedance grounding system. The breakers are designed to trip quickly in response to a ground fault, isolating the fault and preventing further damage. The breakers are also coordinated with the downstream protection devices to ensure selective tripping. This means that the breaker closest to the fault will trip first, while upstream breakers will remain closed, minimizing the extent of the outage. In conclusion, the 12,470 volts impedance grounded system is a carefully designed electrical system that provides multiple layers of protection against faults and other abnormal conditions. The system is designed to protect equipment, reduce arc flash hazards, improve system stability, and ensure compliance with applicable codes and standards. The 36 ohms impedance, limiting the fault current to 200 amps, is a carefully selected value that balances the need for effective fault detection and isolation with the desire to minimize the risks associated with high fault current.